Hello there, and welcome to the Sleepy Science Channel. Tonight, we are drifting into the magnificent realm of solar systems, where worlds, stranger than you can imagine, exist in a cosmic dance of time and gravity. Our own solar system is only one story in a vast library of celestial arrangements, each star surrounded by its own family of planets, moons, rings, and mysteries. Out there, in the silent dark, are systems of twin suns, molten planets, and worlds floating free in the endless cosmos. This is not just a journey through space, it is a journey through wonder, into the hidden architecture of the universe. The things we will discover are not only strange, but beautifully real. These faraway systems might challenge what we think life needs, or what a planet even is. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Let the night sink around you and allow your mind to settle. Let's begin. Some solar systems have planets orbiting two stars. Imagine sunsets arriving in pairs and tides pulled by a duet of suns. In circumbinary systems, a planet loops around both stars at once, threading a path through shifting gravity that looks more like a braided ribbon than a simple ellipse. Stability is possible because gravity, although complex, can settle into repeating rhythms when distances and masses fall within certain ranges. The skies would wax and wane in brightness as the stellar partners eclipse or drift apart from the planet's perspective, painting seasons unlike anything on Earth. Formation studies suggest that dust and ice can still gather into planets, even amid the push and pull of a binary dance, though growth may pause and resume as spiral waves sweep through the disk. These worlds demonstrate nature's flexibility. Where physics allows a pocket of order, matter finds a way to congeal. Their existence widens the stage for potential climates, atmospheres, and perhaps someday, the chemistry of life. There are solar systems where planets orbit in the opposite direction. Retrograde orbits flip intuition on its head. Instead of following the spin of their star, some worlds swing the other way, as if rewinding the cosmic clock. This backwards motion can arise when a planet is tilted by a passing companion, torqued by a skewed disk, or jostled during youthful gravitational scuffles. The result is an orbital plane, misaligned with the stellar equator, sometimes by a little, sometimes by a lot, and occasionally fully reversed. Such geometry reshapes weather and tides because day and year tug in competing directions. It also records a system's history like a scar, preserving clues about collisions or distant perturbers that once wandered close. By reading these tilted paths, astronomers reconstruct ancient dramas that ordinary orbits would hide. Each retrograde world is a case file from a celestial detective story, proving that planetary destinies are not always scripted by the neat spin of their newborn star. One in every 5 sun-like stars may have an Earth-sized planet. Statistical surveys of dim starlight dips reveal a quiet abundance of small worlds. When researchers correct for vantage point and instrument sensitivity, a striking pattern emerges around stars similar in mass and temperature to our own. Roughly a fifth appear to host at least one planet near the size of Earth, and many lie in or near temperate zones where liquid water could persist under the right conditions. This does not guarantee oceans or breathable air, but it transforms the search from a hunt for rare jewels into a methodical cataloging of nearby possibilities. With each transit measured and each wobble mapped, candidate worlds step forward for deeper study. Future telescopes will sift their atmospheres for molecules that shimmer with the signatures of clouds, winds, and perhaps biochemistry. The implication is profound. The night is not empty. It is punctuated by countless small shores, waiting for us to learn their weather, their rocks, and their stories. Some planets wander without a star, set adrift by gravitational encounters or never tethered to a sun in the first place. Rogue planets roam the interstellar dark. Without a nearby star to warm them, they are lit only by starlight from afar and warmed by their own leftover heat and radioactive decay. Their skies hold eternal night. Yet they may carry thick insulating atmospheres or buried oceans beneath ice, sustained by internal warmth and tidal stirring during close flybys of other bodies. Detecting these drifters is hard because they do not silhouette a parent star, but careful surveys can catch their faint glow or the fleeting brightening they cause when passing in front of distant starlight. Their existence shows that planetary birth and eviction are common outcomes of crowded young systems. These lonely worlds turn interstellar space into a subtle archipelago, a scattered fleet of cold islands drifting between the lamps of the galaxy. We have detected solar systems that are almost as old as the universe. Some stars formed when the galaxy was young, enriched by only a few ancestral explosions. Around these ancient suns, astronomers have found the fingerprints of planets. Their chemistry is sparse in heavy elements compared with modern stars, yet still sufficient for dust to clump and build worlds. These venerable systems have quietly orbited for billions upon billions of years, surviving cosmic mergers, tidal shuffles, and waves of starbirth. Their planets, if they still possess atmospheres, have weathered epochs beyond any saga on Earth, giving time a chance to test every possible climate tune. They are time capsules, preserving an early recipe for planet formation that challenges models built from our present-day neighborhood. Studying them connects the first chapters of cosmic history with the planetary diversity we see nearby, proving that world-making began soon after the first stars lit up and has been humming along ever since. Planets can migrate from their birthplace over billions of years. Worlds do not always stay where they first took shape. As young planets exchange momentum with the gas and dust of their natal disks, they can drift inward or outward, sometimes drastically. Later, after the gas clears, gravity games continue as planets tug on one another, trading energy until their orbits stretch, shrink, or even swap places. This slow reshuffling can move an icy giant into a warmer realm or park a giant world close to its star, reshaping the climate of every neighbor. Migration sculpts resonances, clears belts, and can trigger showers of comets that deliver water and organics to inner worlds. It also explains why so many systems defy a simple inside rocky, outside icy pattern. Planetary systems are living architectures, molded by friction and gravity, with final layouts that remember the currents and encounters of their youth long after the original disk has vanished into starlight. Some solar systems are more crowded than ours. Compact families pack several planets inside an orbit smaller than that of Mercury, each circling in days or weeks. Their spacing can be tight yet stable, like pearls on nested strings, because the planets formed together and settled into balanced configurations. In such places, neighboring worlds loom large in the sky, waxing from disks to crescents within a single week. Close quarters amplify tides, stir atmospheres, and create rhythms where conjunctions repeat like a metronome. Crowding does not mean chaos if masses and distances fall into harmonious ratios that prevent near misses. These systems reveal that nature often prefers efficiency, building many medium worlds rather than a few giants and spreading them across snug lanes. Their climates and compositions may vary dramatically from world to world despite the shared star, offering laboratories where a single sunlight feeds a bouquet of planetary experiments arranged almost shoulder to be shoulder. Solar systems can form with no rocky planets at all. If a disk is poor in heavy elements, or if giant worlds form early and hoard material, the inner regions may never assemble durable rock. Instead, gas and ice dominate, yielding a family of mini Neptunes or gas giants with only small, solid cores. In such systems, heat from the star sculpts puffy atmospheres, while distant cold preserves rings and moons carved from icy debris. The absence of terrestrial surfaces transforms everything about habitability and geology. There are no continents to drift, no volcanoes to recycle crust, and no shorelines to cradle oceans. Yet chemistry still thrives in clouds and on the surfaces of moons, and magnetic fields can shield deep atmospheres from stellar tempests. These rockless families demonstrate that planet formation is not obligated to produce Earth analogues. The universe experiments with ensembles where air and ice are the main stage, while stone plays only a hidden supporting role. We have found solar systems where planets orbit in perfect harmony. Resonant chains lock worlds into synchronized motion, where for every set number of laps by one planet, a neighbor completes another exact count. This clockwork keeps orbits from crossing and can persist for immense spans if no large disturbance arrives. The pattern often forms as planets migrate through the disk, capturing one another into step, like dancers adjusting to a shared rhythm. Harmony leaves fingerprints in the timing of transits and the subtle tugs planets exchange, allowing astronomers to weigh them and probe their structures. For inhabitants, if any exist, the heavens would present regular meetings of bright companions, predictably spaced like notes in a repeating melody. Such systems show that gravity, when given time and gentle friction, can compose stable music from dust and gas. The result is not rigid, but resilient, a natural cadence that reveals the history of migration written into the beat of the years. Some solar systems are full of planets that are all about the same size. In our solar system, the planets vary dramatically in scale, from tiny Mercury to massive Jupiter, but elsewhere, the story can look very different. In several observed systems, all of the known planets are unexpectedly close in size, as though stamped from a cosmic mold. These worlds usually fall between Earth and Neptune in diameter, forming a family of super-Earths or mini-Neptunes lined up in tight orbits. Their surfaces and atmospheres, however, can still differ wildly depending on their position relative to the star, the chemistry of the protoplanetary disk, and the histories of collision and migration that shaped them. This kind of uniformity suggests formation conditions that distribute material more evenly, or gravitational interactions that keep competing planets in check. Such systems challenge our sense of what is normal. Instead of a few giants and a few small ones, the universe may prefer symmetry. They open questions about whether life-bearing stability might be more common in evenly balanced systems, where no single world dominates the gravitational landscape. There are solar systems where planets skim so close to their stars, but metal can vaporize. Some planets race around their stars at distances so short that a full year lasts only hours or days, and daytime temperatures can soar high enough to vaporize iron, silicates, and other metals. On these ultra-hot worlds, rocky mountains might never form, because the ingredients for stone can sublimate directly into atmosphere. Winds whip metal vapor from the day side to the night side, where it condenses into glittering mineral clouds that might rain molten droplets back toward the surface. These extreme environments reveal the outer limits of planetary survival under fierce stellar radiation. They also teach us how atmospheres behave when chemistry is pushed far from familiar ranges, creating exotic weather cycles that have no counterpart on Earth. The existence of such worlds shows that planet formation does not avoid the furnace. It adapts to it, building strange spheres that endure in places we once thought entirely hostile to solid matter. we have found solar systems with planets that have no atmosphere. Not every world manages to cling to its surrounding veil of gases. Some planets are being stripped bare by the relentless onslaught of stellar winds, radiation, and gravity. Close-orbiting rocky planets are especially vulnerable, with particles blasted from their surfaces into space until little remains but naked rock. Without an atmosphere to moderate temperature, the dayside can bake while the nightside freezes, locked in a brutal tug between scorching light and icy shadow. The lack of air also means no weather, no protection from meteoroid impacts, and no medium for sound to travel. Yet the exposed surface becomes a direct record of the world's history, unclouded by erosion or chemistry. By studying these stark bodies, astronomers learn how atmospheres are lost, what roles magnetic fields play in shielding planets, and how fragile the balance of pressure and temperature can be. Even in their silence, airless planets speak volumes about the struggle to hold onto a sky. Some planets form far from their star, and only later move inward. A planet's birthplace is not always its final address. Far from a star, in the cold outskirts of a young disk, ices and dust can clump more easily, building hefty cores that later drift inward like rafts on a river of gas. This slow migration can happen through drag from the disk itself or gravitational nudges from neighboring worlds. A giant planet born in frigid space might eventually settle close to the star, becoming a hot Jupiter that could never have formed in its current location. This journey dramatically reshapes the architecture of the system, potentially sweeping aside smaller worlds or stirring belts of debris into chaotic showers. The inward traveler can also trigger resonances that lock other planets into synchronized paths. By tracing these migratory footprints, researchers decode the hidden past of systems that look static today. Planetary placement is a snapshot, not a birth certificate, and many worlds carry the memory of a long inward voyage beneath their clouds. Solar systems can be destroyed when stars become supernovas. When a massive star reaches the end of its life, it can explode with a brilliance that outshines entire galaxies for a brief moment. This detonation, a supernova, unleashes shockwaves powerful enough to tear apart nearby planets, vaporize atmospheres, and hurl debris into interstellar space. Even worlds not directly shattered may be sterilized by intense radiation, their chemistry rewritten in an instant. The blast can also carve expanding bubbles through the surrounding gas, triggering star and planet formation in distant regions, while ending it abruptly in the star's own yard. Some planetary fragments might survive as orphaned asteroids or molten cores, wandering the void without a sun. Studying these cataclysmic endings offers a glimpse into the recycling of cosmic material, since the heavy elements forged in the dying star will eventually seed new systems. Solar systems are not eternal. They are chapters in a cycle of creation and destruction written across the galaxy. There are solar systems with planetary rings bigger than stars. Rings are not just for Saturn. Some exoplanets boast ring systems so vast that their total diameter would dwarf even a medium-sized star. These colossal structures may form from shattered moons, captured comets, or leftover debris that never coalesced into a companion. When the planet transits its star, the rings can block light long before and after the planet itself, creating peculiar dips in brightness that first alerted astronomers to their scale. The sheer size of these rings challenges models of stability because such wide disks must resist collapse, spreading, or evaporation over millions of years. Their presence hints at dynamic recent histories, perhaps involving tidal breakups or colossal impacts. If a moon forms within such a ring, it may eventually clear a lane and grow into a fully fledged companion. These oversized halos are reminders that even familiar features like rings can reach breathtaking proportions when gravity and time have the right raw materials. Some solar systems contain moons larger than Earth. Moons are not always minor companions. In some distant systems, a satellite can rival or exceed Earth in size, orbiting a giant planet like a world in its own right. These exomoons may harbor atmospheres, oceans, and complex geology powered by tidal heating from both the planet and the star. Their day length depends on the balance of orbital motion and rotation, creating unusual cycles of light and shadow. Detecting such moons is challenging because their signals blend with those of their host planets, but subtle timing shifts and flickers of starlight offer clues. If confirmed, these giants would expand the concept of habitable zones to include not just planets, but their satellites. A moon with Earth-like mass and water could thrive under the protective magnetosphere of a parent planet, benefiting from both stellar and reflected light. The discovery of such a place would redefine where we look for life and how we imagine homes beyond Earth. We have found solar systems with planets that have no moons at all. Some planets roam their orbits utterly alone, without even a small captured rock to accompany them. The absence of moons can result from violent pasts, where collisions ejected or destroyed early satellites, or from quiet births in regions of the disk too barren to build them. Without moons, a planet's axial tilt may wobble more through time, leading to erratic seasons and climate swings. Tides are gentler, reshaping coastlines more slowly and reducing tidal heating that can fuel geological activity. The night sky would appear stark and empty, with no secondary light to soften the dark. Yet the solitude of these planets offers a pristine laboratory for studying internal dynamics without the complicating tug of a companion. Their very emptiness poses questions about the ingredients and processes that favor moon-making. In the great variety of solar systems, even a missing moon tells a story about chance, collision, and cosmic scarcity. Some planets have moons that formed before their planet did. In rare cases, a moon may predate the planet it orbits, born as an independent body in the protoplanetary disk, or captured from passing debris long before the main world finished assembling. Later, as material gathered into the planet, gravity pulled the older object into a stable orbit, turning a former wanderer into a satellite. Such ancient moons carry chemical and isotopic signatures that differ from their host planet, preserving a record of earlier conditions in the disk. Their craters and surface layers might reveal impacts and radiation exposure from eras the planet never experienced. This reversal of roles blurs the line between planet and moon, showing that order in a solar system is often a matter of timing and capture rather than strict hierarchy. Studying these mismatched pairs deepens our understanding of how bodies exchange places and how early formation stages can overlap in surprising ways. The first exoplanets were found orbiting a dead star. Before planets were discovered around sun-like stars, the groundbreaking detections came from a pulsar, the dense spinning core left after a supernova. This stellar remnant emits beams of radio waves with clock-like regularity. Tiny deviations in the timing of those pulses revealed the gravitational pull of orbiting planets, bodies that somehow survived or reformed after the star's explosive death. These worlds endure in a realm flooded by radiation and bathed in the eerie glow of a rapidly rotating neutron star. Their existence proved that planets can arise in the most unlikely environments, and that planet formation or recycling can happen even after cataclysm. The discovery shattered assumptions and opened the field of exoplanet science, showing that nature writes planetary stories in places far stranger than our gentle solar neighborhood. Every subsequent find traces its lineage back to those first worlds circling a dead sun. Some solar systems have planets that orbit faster than a day on Earth. In some distant solar systems, a planet can complete a full orbit in less time than it takes Earth to experience a single sunrise and sunset. These ultra-short period planets are locked so close to their stars that they race around them in a frantic loop, sometimes in less than 10 Earth hours. Their motion is controlled by extreme gravity and blazing heat, leading to atmospheres that boil away or shift constantly between vapor and plasma. Tidal forces stretch and squeeze them, creating internal friction that can melt rock and drive volcanic activity. If one could stand on the surface, the star might fill half the sky, and the speed of orbit would cause dramatic changes in light across the landscape, even though the planet often remains tidally locked, with one perpetual day side and one endless night side. These blisteringly fast worlds challenge our expectations about orbital stability and show just how far the universe is willing to push the boundaries of what a planet can endure. We have detected exoplanets that are mostly water. Some worlds beyond our solar system appear to be made almost entirely of water, existing as global oceans without continents or land masses. Their dense, pressurized layers may transition from liquid to exotic forms of ice unseen on Earth, such as Ice 7 or Ice 10, where water molecules crystallize in cages under unimaginable pressure. Above this watery core lies an atmosphere filled with steam or vapor, possibly enveloped by thick clouds that reflect a high percentage of the star's light, giving the planet a pale blue halo when observed from afar. These water worlds may experience constant storms, with winds crossing oceans thousands of kilometers wide without interruption. The idea that a planet can form and survive without a significant rocky crust beneath it expands the definition of habitability. If life evolved there, it might have no concept of land at all, thriving in vast underwater ecosystems completely alien to anything humanity has imagined, where tectonics and volcanism happen beneath kilometers of crushing sea. There are solar systems where the planets are made of diamond. Some planetary bodies have been detected with densities and compositions that imply they are rich in carbon, and under the right temperature and pressure, carbon can crystallize as diamond. These so-called diamond worlds likely formed around stars that were themselves composed of carbon-rich material, allowing for carbon to dominate the early planetary disks. As planets cooled and compressed, their interiors may have transformed into vast layers of solid diamond, capped by molten carbon oceans or even carbon dioxide-rich atmospheres. Temperatures on the surface might be sweltering or freezing depending on distance from the star, but deep below, a glittering mantle of diamond could extend for thousands of kilometers. Such worlds could contain more diamond than has ever existed in the entire history of Earth, turning the concept of treasure into something cosmic. They remind us that beauty, value, and geology take on unimaginable forms across the galaxy, where elements follow universal laws, but the outcomes are anything but ordinary. Some planets orbit so close to their star that a year lasts only hours. In several star systems, astronomers have found planets so close to their host stars that their orbital periods are mere hours long. They complete entire revolutions in the time it takes us to eat breakfast or sleep through a night. These planets are heated to thousands of degrees on their sun-facing sides, causing rock to vaporize and form atmospheres of mineral gases. Their skies might shimmer with clouds of silicate particles, and metal could condense and rain as droplets of molten iron. Intense radiation strips these atmospheres away continuously, leaving long comet-like tails trailing behind the planet as they race around their star. The gravitational pull is so overwhelming that many are tidally locked, with one hemisphere forever exposed to stellar fire and the other cast in eternal shadow. Their blistering orbits hurtle through warped space-time, illustrating the sheer range of planetary environments that can exist when nature puts the laws of physics to their most dramatic test. We have detected planets as light as cork. Among the vast catalogue of exoplanets, some are so puffy and lightweight that they would float in water if such a thing were possible on a cosmic scale. These planets have extremely low densities, often less than that of Cork due to their giant sizes, and bloated atmospheres filled with hydrogen and helium. They are known as superpuffs or cotton candy planets, orbiting close to their stars, where stellar heat expands their gaseous envelopes to enormous volumes. Despite their impressive radii, their total mass might only equal a few Earths, making them incredibly fragile. The slightest increase in stellar radiation or a close encounter with another object could strip away their atmospheres completely. This strange state challenges our understanding of planetary formation, suggesting that these worlds either formed quickly with vast frozen cores or accumulated gas slowly in gentle environments before drifting inward. Their existence shows how delicately balanced a planet can be, surviving only because the universe allows it a rare and narrow set of circumstances. Some solar systems have planets far more massive than Jupiter. Jupiter is the heavyweight champion of our solar system, but other systems contain planets that make it look modest by comparison. These super-Jupiters can be 10 or even 20 times more massive, and yet still qualify as planets because they are not quite large enough to ignite nuclear fusion and become stars. Their immense gravity can dominate a system, steering the orbits of neighboring planets, sculpting debris belts, and even preventing smaller worlds from forming at all. Their atmospheres may be crushingly dense, filled with exotic chemistry driven by immense internal pressures and heat left over from their formation. Some of these giants orbit close to their stars, becoming searing hot and glowing faintly in infrared wavelengths, while others roam far out in the frozen dark with cloud tops colder than any temperature on Earth. The scale of these worlds stretches the word planet to its limit, showing that even within a category, the universe permits extraordinary diversity. We have found planets that orbit more than one star at a time. While our Earth orbits a single star, some planets follow paths around multiple suns, circling them as a group. These circumbinary or circumultiple worlds experience complex gravitational ballet, where the star system itself twists, turns, and wobbles as the planet maintains a wide, stable orbit. The skies of such a world might feature 2 or 3 sunrises and sunsets each day, their positions shifting over time as the stars interact. Temperatures on the surface rise and fall in strange cycles defined not only by distance to a primary star, but by the shifting influence of its companions. These planets survived a chaotic birth, where the turbulence of multi-star formation could have easily ejected them into space. Instead, they found balance, circling a gravitational center that drifts through the cosmos like a living system. These planets show that stability is still possible in what seems like chaos, and that the universe's rules always find a way to carve harmony out of complexity. Some solar systems are hidden inside star clusters. Star clusters are dense neighborhoods where thousands of stars form together in a single burst, packed so tightly that the night sky on any planet would glow with countless suns. For a long time, astronomers wondered if planets could even survive in such busy environments, where passing stars might strip them away or disrupt their orbits. Yet observations have revealed planets nestled within these stellar cities, orbiting their parent stars in relative peace. These planets may experience close encounters with other stars every few million years, which might change their climates or even their positions slightly, but many endure for billions of years. Their existence suggests that planetary formation is robust, capable of unfolding even in crowded nurseries, where radiation, gravity, and motion collide. To stand on such a world would be to witness a sky blazing with starlight, where the cosmos never grows dark, and where planetary life shares space with the furnace of young suns. Solar systems can be disrupted by passing stars. Stars travel through the galaxy like ships on a vast ocean. and sometimes their paths bring them dangerously close to one another. When a passing star swings near a solar system, its gravity can tug on planets, asteroids, and comets, reshuffling or even ejecting them into interstellar space. This kind of disturbance may send icy bodies plunging inward to bombard inner planets or pull distant worlds into new orbits that change their climates dramatically. Some planets might be completely lost, slung into the void to become rogue wanderers. These encounters are rare on human timescales, but practically guaranteed over the lifetimes of stars. The fossil record of such an event may be seen in oddly tilted or eccentric orbits, suggesting that the quietness of our solar system might itself be a stroke of luck. Disruptions remind us that solar systems are not isolated islands, but travelers in a dynamic galaxy, shaped by encounters we cannot yet see. Some planets form in the debris disks left behind by dead stars. When a star dies gently, shedding its outer layers to become a quiet white dwarf, it sometimes leaves behind a swirling disk of gas, dust, and shattered remains of earlier planets. Within this disk, new planets can begin to form, recycling the materials of a previous generation. These second-chance worlds may contain elements forged in the heart of the dying star, giving them unusual chemistry or dense metallic cores. Their parent star no longer burns like a main-sequence sun, but glows faintly with leftover heat, casting dim light across a landscape that might still hold warmth deep underground. The idea that planets can be born from the ashes of their predecessors expands the life cycle of solar systems, proving that destruction can also be a kind of creation. These reborn worlds occupy a twilight realm of astrophysics, where the end of one cosmic story becomes the prologue to another. Solar systems can be born from collisions between giant clouds of gas. When two enormous clouds of gas drift through a galaxy, they sometimes intersect with enough force to trigger star formation. The collision compresses hydrogen, helium, and interstellar dust, causing pockets within the clouds to collapse under their own gravity. These compressed pockets become the cradles of new stars, each potentially surrounded by disks where planets may emerge. This dramatic beginning leaves fingerprints in the systems that form. The initial turbulence can result in planets with wildly tilted orbits, unusual spacing, or unexpected chemical makeups. Some planets may form quickly and grow massive before the chaos settles, while others emerge later from leftover debris. Even the stars themselves might be born as siblings, traveling through space together, each with its own retinue of worlds. This kind of cosmic collision shows that star and planet formation is not always calm. Sometimes, it begins with an interstellar impact that sets the stage for entire families of worlds. There are solar systems where dust clouds never fully become planets. Not every protoplanetary disk coalesces into solid worlds. In some solar systems, the dust and gas remain in a suspended swirl for billions of years. These translucent, glowing clouds reflect the light of their star and reveal a stalled process of planetary birth. Perhaps the disk lacked enough mass, or early disturbances prevented larger bodies from forming. In other cases, unseen planets may lurk within, shepherding the dust into rings and lanes without ever clearing a full path. These half-formed systems act like time capsules, preserving the raw ingredients of planet-making long after neighboring systems have moved on to rocky surfaces and atmospheric storms. They also replenish the galaxy, sending dust back into interstellar space where it might one day seed the next generation of stars. Studying these lingering clouds helps scientists understand the fine balance required for planets to emerge, and why some stars never end up with full-fledged worlds at all. Some planets orbit far beyond the reach of their star's light. In the vast outskirts of certain solar systems lurk planets so distant that their host star appears merely as a bright speck in the sky. These worlds move through regions where warmth from the star scarcely reaches, plunging their surfaces into bitter cold. Any atmosphere they retain may freeze into layers of ice, stacking over centuries until only slivers of gas remain aloft. Yet some of these distant giants may harbor internal heat from radioactive decay or the lingering energy of their birth, creating subsurface oceans beneath frozen crusts. Their slow, monumental orbits can take thousands of Earth years to complete, making their seasons longer than the entire history of human civilization. These remote worlds remind us that the architecture of a solar system can stretch far beyond the cozy zones where warmth and light create familiar landscapes. In those distant reaches, alien chemistry and endurance replace sunlight as the ruling forces of planetary life. We have found planets that orbit their star on a tilted axis. Most planets orbit roughly in line with the equator of their star, but some defy this pattern, tilting wildly above or below the stellar plane. These misaligned orbits suggest a chaotic past, perhaps involving collisions with other planets, the gravitational shove of a nearby star, or the influence of a warp in the early disk where the planet first formed. For inhabitants, if such a world fosters life, the seasons would be strange and unpredictable. The star might rise far to the north for decades, then slowly drift to the southern horizon as the planet continues its tilted path. Climate zones could migrate across the surface in long cycles, shaping evolution and geography in unique ways. These skewed orbits are clues to forgotten upheavals in a solar system's early history, offering a rare glimpse into the chaotic ballet that shaped worlds long before they found their present paths. Some solar systems have planets with highly eccentric orbits. While Earth moves in a mostly circular path, many exoplanets travel on stretched, elongated tracks that carry them from blistering proximity to their star out into frozen darkness. These eccentric orbits can be caused by gravitational encounters with other planets, stellar flybys, or leftover turbulence from formation. The surface of such a planet might experience seasons more extreme than anything on Earth. For part of its orbit, it could be scorched by intense radiation, its atmosphere swelling with heat and storms. Later, as it retreats into the dark, that same atmosphere might freeze and condense, creating cycles of evaporation and frost that reshape the world every few centuries. These immense temperature swings can fracture rocks, churn oceans, and sculpt landscapes with unforgiving power. Eccentric planets defy the calm rhythms we associate with orbital motion, revealing that even the steady heartbeat of a year can be bent and twisted by gravity's invisible hand. Planets can be torn apart by the gravity of their star. When a planet orbits too close to its star, the tidal forces can exceed the strength of the planet's own gravity. Layers of rock and atmosphere begin to peel away, forming streams of vaporized material that spiral into space. Over time, what was once a solid world may dwindle into a remnant core surrounded by clouds of dust and glowing gas. Astronomers have detected such doomed planets by the trails they leave behind, like cosmic breadcrumbs marking their final journeys. These shredded worlds may become rings, dust belts, or even fuel future planets in the same system. The process is not quick. It may take millions of years for a planet to fully unravel under the relentless pull of its sun. Yet the result is always the same, a reminder that gravity giveth and gravity taketh away, sculpting the fates of planets with the same quiet certainty that ignolds galaxies and stars. Some solar systems contain asteroid belts far larger than our own. Our solar system has the asteroid belt between Mars and Jupiter, but other systems feature belts hundreds of times more massive, filled with objects ranging from dust grains to mountain-sized fragments. These colossal belts may be the wreckage of worlds that never formed, or the remains of past collisions that shattered planets to pieces. The sheer volume of debris can fill the sky of any nearby planet with glittering shards and streaks of fire, especially if the system is still young and collisions are frequent. Such belts also serve as archives, preserving the chemical makeup of the original disk, long after larger bodies have evolved. They may even seed life on inner planets, delivering water and organic molecules during periods of heavy bombardment. These oversized rings of stone and ice reveal the unfinished business of planet making, where the leftovers of creation linger and participate in the cosmic story for eons. There are solar systems with 2 or more habitable zones. The habitable zone is usually imagined as a single band where liquid water can exist on a planet's surface. But in some solar systems, there may be multiple such regions. A star with a broad temperature range or a binary star system with 2 sources of heat can create overlapping or distinct habitable bands. One region might support rocky planets with temperate conditions, while another farther out could allow gas giants with watery moons to harbor life. The idea of multiple habitable zones expands the canvas for potential biospheres, suggesting that life could arise in many more places than previously thought. These zones shift over time as stars grow hotter or dimmer, giving planets temporary windows where conditions are just right. The presence of more than one such band makes these systems rich targets for exploration, hinting at the extraordinary adaptability of nature when given the right conditions in more than one neighborhood. The habitable zone can move as a star grows older. Stars change over billions of years, growing brighter and hotter as they burn through their fuel. This evolution causes the region where liquid water can exist to drift outward. A planet that was once comfortably temperate may become too hot, while another frozen world farther out might thaw into a new oasis. Such planetary migrations through habitability can create epochs of life, separated by long ages of dormancy or extinction. For a world like Earth, the habitable window is temporary, slowly edging toward a distant future where oceans boil and only the poles remain cool. These shifting zones reveal that habitability is not static, but a moving target, shaped by stellar aging and planetary endurance. Understanding this dynamic helps scientists search for life on planets that may only now be entering their golden age, even if they once lay beyond the reach of warmth and water. Some solar systems form in star-forming nebulas. In the brightest regions of the galaxy, vast nebulae glow with ionized gas and starlight. These stellar nurseries are where solar systems are born in great numbers, as filaments of gas collapse into clusters of stars that each gather disks of dust and ice. The intense radiation from nearby massive stars can sculpt these newborn planets, stripping away atmospheres or igniting chemistry in ways impossible in quieter neighborhoods. The sky of a planet forming in such a place would blaze with shifting clouds of red and blue, lit by the ultraviolet glow of enormous suns. Each world carries the imprint of its birthplace. Rare metals from ancient supernovas, complex molecules from earlier generations of stars, and scars from radiation storms that batter its early surface. Nebula-born systems remind us that planetary creation is not always gentle. Sometimes it happens in the shadow of giants, under a sky that burns with the fire of 1,000 stars. Solar systems may begin forming even before a star is fully born. Before a star's core ignites into steady nuclear fusion, while it is still gathering mass from the surrounding cloud, its gravity can already begin shaping a disk of swirling dust and gas. In these early phases, tiny grains collide and stick together, forming pebbles, then boulders, and eventually the seeds of planets. Even as the protostar flickers and contracts, these planetesimals carve lanes through the disk, accreting material and casting shadows of future worlds. In this twilight period, before the star settles into stable burning, properties like disk temperature, magnetic turbulence, and chemical gradients and predetermine what sort of planets will form: rocky, icy, gaseous, or nothing at all. The solar system's story begins not with the star's first light, but with the quiet choreography of dust spirals and invisible forces. By the time the star fully awakens, its planetary children may already be well on their way to adulthood. There are solar systems that are perfectly aligned and others that are chaotic. Some solar systems possess a serene symmetry, where all planets orbit neatly in the same plane, aligned with the gentle spin of their star. Others are wild mosaics of tilted, twisted, and looping paths that defy the tidy logic seen in our own neighborhood. In these chaotic systems, planets may orbit at sharp angles to one another, circle above or below the star's equator, or even retrograde against the star's rotation. These patterns often arise from ancient upheavals, giant impacts, gravitational encounters with neighboring stars, or turbulent collapses in the gas disk that never fully settled. The result is a snapshot of cosmic memory, an imprint of every force that shaped the system. By studying both the orderly and the unpredictable, astronomers learn that nature's blueprint allows for beauty in balance and in disorder, proving that both harmony and chaos are part of the cosmic design. Some planets never finish forming before their star burns away the material. Planetary formation is a race between growth and loss, and not all participants make it to the finish line. Around some stars, the intense heat and radiation of the young star's ignition burn away the last wisps of the protoplanetary disk, before all the planetesimals can fully assemble into planets. These unfinished worlds can remain as massive asteroids, scattered rubble piles, or moon-sized bodies, too small to round themselves into spheres or hold stable atmospheres. Their surfaces bear the scars of collisions that were never followed by the gentle smoothing of gravity. Long after the gas is gone, these fragments drift in silence, reminders of what might have been if only time had stretched a bit further. Studying these incomplete planets offers insight into how delicate the balance of timing and environment is in planet formation. Even the most promising beginnings can be cut short when a young star turns fierce too quickly. We have detected solar systems forming around baby stars. Baby stars, or protostars, glow faintly as they gather mass and evolve toward the main sequence. Around them, disks of dust and gas whirl in thick, luminous bands, warmed by the growing star's soft energy. In these warm, churning disks, astronomers have detected the distinctive gaps and rings that mark the early stages of planet formation. Planets in these systems might still be molten, layered with hot ices, or wrapped in thick nebular atmospheres. The entire system is a moving portrait of creation, dust grains spiraling inward, ice giants carving glowing trails, and gas knotting into the futures of weather, oceans, and sky. Observing these baby systems in real time is like watching a time-lapse of our own solar system's youth, revealing not just what we are, but what we were. Every click of a telescope shutter catches a piece of that cosmic childhood we can never relive. Some solar systems show signs of full planetary destruction. In some star systems, astronomers have found overwhelming evidence that planets once existed, but no longer do. The most obvious clues are glowing rings of metallic dust, polluted white dwarfs filled with silicon and iron, or clouds of vaporized rock orbiting too close to the star to be natural. These are the scattered remains of worlds ripped apart by tidal forces, obliterated in stellar expansion, or shattered by violent collisions. Even moons or minuscule pebbles may still be present, silently tracing the outlines of what once was a thriving system of worlds. Planetary destruction on such a scale reminds us that solar systems are fragile, temporary arrangements. Their stories include not just birth and evolution, but decay and erasure. And yet, even in destruction, they contribute material that may one day give rise to new planets, reincarnating their atoms in the next generation of stars. Solar systems can form in the galactic core. The heart of a galaxy is not empty. but densely packed with stars, gas, dust, and immense gravitational forces. Amid this chaos, solar systems can form, though their environments are dramatically different from ours. Stars born in the galactic core may be bombarded by radiation from nearby supernovas or jostled by the gravitational tides of passing stellar neighbors. Disks forming around these young stars are rich in heavy elements forged by previous generations, allowing planets to form quickly and often with high metallic composition. These planets, if they survive long enough, might develop unusual atmospheres or compressed cores due to frequent gravitational disturbances. Life, if it arises, would adjust to a sky filled not with isolated pinpricks of light, but with an almost solid wall of nearby suns. Solar systems at the core remind us that planet formation is possible everywhere, even in the busiest, noisiest corners of the cosmic city. Some planets have atmospheres made entirely of metal vapors. On certain ultra-hot exoplanets, the temperatures are so extreme that metals like sodium, magnesium, and even iron vaporize into gases. These metallic atmospheres shimmer like liquid mirrors, reflecting and refracting light into brilliant spectral lines that telescope instruments can detect from light years away. Winds on such worlds might flow at thousands of kilometers per hour, carrying metal vapor from the day side to the night, where it condenses into glittering clouds or even rains down as molten droplets. The skies here are alien in every sense, with lightning storms crackling through metallic haze and no breath of oxygen or nitrogen to soften the air. These shimmering worlds push the definition of an atmosphere to extremes, reminding us that what seems unimaginable on Earth may be entirely ordinary elsewhere. In space, even the air can be forged from fire and metal. We have found planets that may rain glass or rubies. Some planets possess atmospheres rich in exotic silicates and mineral compounds that condense into crystals rather than water. On these worlds, colossal winds can hurl molten particles high into the air, where they cool into shimmering grains of glass or precious gemstones like corundum, the mineral behind sapphire and ruby. As gravity takes hold, these crystals fall like colorful rain, scouring the surface or bouncing across roiling oceans of liquid metals. The combination of fierce winds, extreme temperatures, and unique chemistry creates landscapes that sparkle not with frost or dew, but with shining treasure torn from the sky. On such planets, storms can become legends, turning the weather into a weapon or a wonder. These places remind us that beauty and danger often walk hand in hand in the cosmos, turning the elements we know into art beyond earthly imagination. Some solar systems contain planets that are tidal locked. Tidal locking occurs when a planet's rotation slows to match its orbit, leaving one side forever facing the star and the other plunged into constant night. This is common among worlds orbiting close to dim, cool stars, where gravitational tides act quickly. The daytime hemisphere bakes under unending starlight, while the night hemisphere chills to near absolute zero, forming a planet cut in two by shadow. In the twilight band between, strange weather patterns swirl, transporting heat and gases in endless cycles. Oceans might cluster along this terminator zone, while life, if it exists, would adapt to a sky where the star never rises or sets. Tidal locking challenges our traditional picture of habitability, but recent models show that with the right atmosphere or oceans, such planets could support stable climates and even thriving ecosystems. Not all dual worlds are lifeless. Some simply bear climates shaped by relentless starlight and eternal night. Some planets spin so fast they almost break apart. A few exoplanets rotate so rapidly that their equators bulge outward, stretched by centrifugal force to the brink of instability. These planets may complete a full rotation in just a few hours, whipping their atmospheres into cyclones and flattening their shapes into oblate spheroids. At these speeds, gravity pulls harder at the poles than the equator, creating wild differences in atmospheric pressure and temperature. If they spun any faster, they would fling material into space or tear apart entirely. The forces at play create firestorms, shock fronts, and extreme auroras, painting their skies in ways we cannot easily imagine. Their dizzying rotation is a clue to their youth or their violent past, perhaps a legacy of collisions or migration that left them spinning like cosmic tops. These worlds are testaments to the boundaries of planetary endurance, where physics writes poetry at the edge of destruction. Some planets reflect so much light, they shine like mirrors. Far from our skies, a handful of worlds shimmer like polished metal, returning an astonishing fraction of the starlight that falls upon them. Their brilliance can come from bright cloud decks seeded with tiny crystals, from vaporized minerals that condense into reflective hazes, or from surfaces glazed into glass by relentless heat. This high reflectivity turns them into beacons that rise and fall in brightness as clouds migrate and storms breathe across the dayside. That flicker is a gift to observers, since changes in glow reveal wind speeds, cloud heights, and even hints of chemistry without a single drop of landfall. Some of these gleaming planets circle so close to their suns that the mirror is a living thing, constantly remade as minerals boil, travel on supersonic winds, and settle again as glittering frost. Others are cooler but mantled in ices or salts that keep them luminous. Each one is a natural signal flare that tells us what its sky is made of. We have found planets that float in almost total darkness. Astronomers have uncovered worlds that travel through space without a parent sun, set adrift during turbulent youth or never bound in the first place. Without nearby starlight, their landscapes are lit only by the faint red warmth of their own interior heat. Any atmosphere becomes a slow blanket, holding what little energy remains while the surface freezes into plains of dark ice. Where pressure grows great, buried oceans may survive under shells of frozen gases, kept liquid by the steady murmur of radioactive warmth in the rock. These planets are nearly invisible, yet they reveal themselves through brief gravitational lensing events, when their mass bends distant starlight for a moment and then slips away. A few are warm enough to glow faintly in infrared light, like embers drifting in a black sea. They are reminders that planet-making is messy and that the galaxy is sprinkled with lonely worlds that carry their nights with them. Some solar systems have planets made of exotic matter. Most planets we know are mixtures of rock, ice, and gas, but theory allows for objects stranger than anything in our solar system. If a collapsing cloud carries unusual chemistry or is exposed to extreme pressure for long periods, matter can settle into states that seldom appear elsewhere. Deep interiors might become crystalline carbon on a colossal scale, or metallic hydrogen that behaves like a sea of electrons. Some scenarios even predict ultra-dense forms of matter that pack more mass into less volume than any ordinary planet could sustain. These bodies would be small, heavy, and fiercely gravitational, with surfaces that swallow meteoroids without a trace. They might form in regions seeded by ancient supernovas, or near compact stars where tides and pressure drive matter into extremes. We have not yet visited such places, but their gravitational pull and the way they affect nearby starlight hint that nature's playbook for building planets is broader than our local sample suggests. We have detected signs of planets being consumed by their stars. A star that swells in old age can swell enough to touch a nearby world. When that happens, gas from the planet spirals inward and leaves fingerprints in the star itself. Astronomers see sudden enrichments of elements like lithium and iron in stellar atmospheres, patterns that do not arise from normal stellar cooking. Some stars also spin faster than expected for their age, as if a recent meal added angular momentum. Around white dwarfs, which are the embers left after a sun-like star expires, heavy elements appear in the thin stellar surface, even though they should sink quickly. The only plausible source is a steady drizzle of planet crumbs and asteroid dust falling in from disrupted orbits. Infrared glows from hot debris rings and tiny dips in starlight that repeat irregularly complete the picture. What we witness is not a single catastrophe, but a menu of endings, each showing how gravity eventually collects what it once allowed to wander. Some planets have magnetic fields far stronger than Jupiter's. Giant planets with roaring interiors can generate magnetic fields that dwarf anything in our solar system. Fast rotation and deep layers of conductive fluid act like a dynamo, turning internal heat and motion into vast invisible shields. These fields trap charged particles and funnel them into poles where auroras bloom large enough to outshine the host star in radio light. Space around such a world becomes a fortress of magnetism, with bow shocks in the stellar wind and tails that stretch for millions of kilometers. The strength of the field hints at the constitution of the interior, perhaps metallic hydrogen under crushing pressure, or salty oceans wrapped around super-Earth cores. When a planet with a powerful magnetosphere skims close to its star, magnetic interactions can even heat its upper atmosphere and change the chemistry of its auroral glow. By listening for those radio murmurs and watching for ultraviolet flashes, we learn to weigh the hearts of distant worlds. There are solar systems with more than one asteroid belt. Beyond many stars lie not one but several belts of leftover building blocks, stacked like nested rings. Each belt carries a different temperature and composition, with warm inner debris rich in rocky fragments and colder outer regions stocked with ices and organics. Gaps between belts are not empty mistakes. They're often the signature of unseen planets that have quietly swept lanes clear or locked dust into resonant patterns. The structure of these belts reveals a history of growth and interruption, of worlds that formed quickly and others that stalled. Collisions within the belts grind larger bodies down into fine dust, which shines in infrared light and outlines the architecture like chalk on a blackboard. When a young system is especially active, that dust brightens and fades on human timescales as smash-ups come and go. In older systems, the belts persist as archives, preserving a record of the materials that once circled far more thickly. Some solar systems form around stars too small to be seen with the naked eye. Tiny stars cool enough to appear as red embers on the cosmic stove are everywhere, and many of them host planets. Their disks are smaller and longer-lived than those around bright suns, which gives small worlds ample time to grow. Orbits snugly close to these stars receive present levels of warmth, even though the stellar light would look dim and red to human eyes. Flares can be frequent in youth, but over long spans the steps towards stability arrive, and atmospheres that are dense or magnetically shielded can endure. Because these stars are faint and common, their planets make up a large share of the habitable real estate in the galaxy. Transits repeat often, which lets observers map atmospheres, seasons, and sometimes weather. From a surface bathed in crimson noon, the parent star would loom large and steady. The possibilities that gather around small fires are not small at all. We have observed planets that orbit inside stellar winds. Every active star breathes a river of charged particles that flows outward in all directions. Some planets circle so near to that breath that their skies are carved by constant particle storms. At the boundary where the wind meets the planetary field, shock fronts form and accelerate particles into auroras that encircle entire hemispheres. The wind strips light gases, sculpts plasma tails, and can even induce electric currents that heat the upper atmosphere from within. These environments are harsh, yet informative. The way a planet resists or yields tells us whether it has a global magnetic field, how dense its air might be, and what volatile elements are present. As the star cycles between quiet and active, the planet's response changes rhythmically. To watch such a world is to see whether that begins at a sun and ends in a sky, a complete circuit from stellar heartbeat to planetary glow. Some solar systems have planets with comet-like tails. Not all tails belong to comets. Some close-in planets shed gas so quickly that a long stream trails behind them, curved by orbital motion and pushed outward by the pressure of starlight. The tail can be made of hydrogen torn from an upper atmosphere, or heavier vapors from rocks that evaporate under fierce heat. When the planet passes in front of its star, the tail starts blocking light before the planet arrives and keeps blocking light after it departs, creating a transit with a drawn-out entrance and exit. Different colors of light are absorbed at different points along the stream, which lets observers separate the ingredients and watch how they change with time. Tails can break into clumps, fade, and regrow as the stellar wind changes. They are living records of escape, showing how a world loses breath to its sun and how quickly a fragile sky can thin. We have found planets that orbit black holes. Worlds can circle the darkest objects in the cosmos, bound not by warmth, but by gravity alone. In such a system, daylight would come from a distant companion star, or from a glowing disk of gas spiraling toward the black hole. Orbits must be wide enough to avoid destructive tides, yet close enough to remain bound against the tug of passing stars. Detection is difficult, so the evidence arrives in pieces. Subtle gravitational lensing events hint that a compact, massive center carries a lighter companion. Flickers in the light of accretion disks suggest an unseen planet, shepherding gas into waves. The physics is stark, but not hostile to stability. If conditions are calm and radiation levels are modest, moons and atmospheres could persist for very long times. In these remote precincts, the ruler is gravity itself, and a planet survives by learning the quiet geometry of a deep well in spacetime. Some planets never experience night at all. On certain worlds, the concept of night does not exist. These planets either rotate so slowly or are tidally locked to their stars, resulting in one hemisphere bathed in perpetual daylight, while the other is frozen in endless shadow. On the day side, the sun never sets, climbing only slightly across the sky as years pass, blazing down with unbroken radiation. Temperatures climb to extraordinary levels. Towering clouds of steam or dust rise from the surface, and winds swirl constantly in convection loops. Vegetation or life, if it ever evolves, would grow without rest under blinding, relentless light. The twilight zone between the two extremes might hold the only refuge, a thin band where the heat of the day and the cold of the night find a fleeting balance. These worlds show that a planet's rhythm, its breathing in and out of light and shadow, is not universal. Some live in eternal day, never knowing the calm of darkness. There are solar systems with planets that glow from their own heat. Some young or massive planets radiate so intensely with internal heat that they shine faintly in infrared or even visible light. These glowing worlds may still be cooling from their violent birth, their interiors churning with molten rock and compressed metals. Others generate heat through tidal friction, pulled and squeezed by the gravity of nearby giants in a perpetual cycle of flexing and release. Their energy oozes outward, creating surfaces that may shimmer with molten lakes, glowing clouds, or burning atmospheres rich in vaporized elements. From afar, these planets appear like miniature stars that orbit larger ones, their warmth creating soft halos in telescope images. In time, they may cool, darken, and settle into familiar silence, but for millions of years, they blaze with the fire of youth. Their heat is a reminder that planets are not merely dark rocks circling suns. Sometimes, they are suns in miniature, carrying their own inner flame. we have detected solar systems that are still swirling with dust. Many solar systems never completely clear the chaos of their childhood. Long after planets have formed, the space between them can remain filled with clouds of microscopic grains, shattered fragments of comets, and shattered rock that reflects starlight in a glowing haze. These dust clouds glow in infrared wavelengths, outlining lanes and arcs, sculpted by hidden worlds or by the gravity of fast-moving giants. In young systems, the dust is thick enough to block or scatter visible light, turning everything into a warm, smoky fog. It can also reveal clues about ongoing collisions, planetary migration, or the birth of moons. In older systems, the remaining dust is a faint echo of earlier violence, made visible only when a nearby star shines through it. These swirling remnants show us that planetary architecture is never truly finished. It settles, shifts, and sometimes grows messy again as worlds collide, decay, or keep forming from dust unclaimed. Planets can form in the shadow of giant stars. Massive stars burn hot and fast, radiating so fiercely that nearby materials are stripped, melted, or pushed away. And yet, in the shadows cast by their enormous disks, or in stable eddies behind dense clumps of gas, planets can still form. Protected from the worst radiation, silicate grains cling together, ice coats tiny pebbles, and larger bodies slowly take shape, even as the parent star burns millions of times brighter than our sun. When the giant finally explodes in a supernova, the shock wave may strip away atmospheres or blast the forming worlds with cosmic rays. But some planets can survive, shielded by timing or orbit, carrying within them materials enriched with heavy elements forged in the star's final moments. These worlds are born in danger, but what remains can be more exotic, more metal-rich, and more dynamic than anything our own system has to offer. They are literal survivors of stellar fire. Some solar systems are slowly being eaten by their star's radiation. In certain systems, the star emits so much high-energy radiation that its planets are stripped of their atmospheres atom by atom. Over billions of years, the gas that once formed thick skies begins to erode, rising into space and drifting like cosmic smoke. Lighter elements escape first, leaving behind heavier particles that may clump or fall toward the planet in strange rains. Some of these worlds shrink visibly, losing mass and changing density as their surface is sandblasted by invisible storms of ultraviolet and charged particles. In extreme cases, the entire planet may vanish, leaving only a rocky core or a sparse ring of dust in its place. These erosive solar winds turn planets into slowly fading memories, their substance carried outward to seed space with fragments of ancient ground and sky. The universe holds no permanence, not even for worlds. We have found solar systems that contain interstellar visitors. Sometimes a frozen wanderer is captured by the gravity of a distant star, trapped in an orbit, and adopted into a new family of worlds. These visitors likely formed around other stars, but were flung outward by violent early events, traveling alone for ages before being pulled in by another sun. Their orbits are often stretched and angled strangely, like relics from another story dropped into unfamiliar company. Their composition may reflect a different chemistry, revealing rare metals, complex ices, or isotopes not found in the native solar system. Long-term studies may show whether they become stable, or whether they will be flung away again after a few million years. Their presence reminds us that the line between stars is porous. Solar systems do not own their objects permanently. Space is a place of exchange, where even planets can change homes. Some solar systems create giant planets in just a few thousand years. The standard picture of planet formation includes slow accumulation, with gas giants taking millions of years to emerge. Yet, in some systems, these colossal planets form in just a few thousand years, ballooning directly from gravitational instabilities in the protoplanetary disk. When a region of gas and dust becomes too massive, it collapses into a hot, dense core that traps material rapidly, creating a gas giant in a single leap rather than a slow climb. These fast-forming worlds may end up far from their stars or may migrate inward quickly, disrupting disk structure and preventing other planets from forming nearby. Their speed may leave them with eccentric atmospheres, layered with ingredients that never fully mixed. These giants are cosmic shortcuts that change everything around them. They are proof that the universe has both patient plans and impulsive designs. Solar systems can form in the wake of supernovas. When a massive star dies in a supernova, it leaves behind not just destruction, but also enrichment. The blast scatters heavy elements into surrounding space, filling clouds with iron, gold, uranium, and other ingredients that cannot form any other way. If that material collapses into new stars, their disks become the cradle for planets rich in metals and volatile compounds. These planets may begin their lives already seeded with radioactive heat sources, complex chemistry, and high-density cores. The shockwave that once shattered the parent star becomes the spark for new formation, creating a family of worlds that carry within them the memory of cosmic death and rebirth. Our own solar system may be such a descendant, since traces of supernova elements still linger in Earth's rocks. Creation, in the cosmos, is often a direct child of destruction. We have found evidence of solar systems forming near black holes. Even in the extreme gravity near a black hole, planets can begin to grow. Stars form in great clouds, and when those clouds happen to lie close to a black hole, the disk around a newborn star may still gather material into spinning lanes of rock, ice, and gas. The gravitational field distorts those lanes, compressing material at some points and thinning it at others. But the process can continue if stability is found. Any planets that do form may orbit a star that itself orbits a black hole, adding layers of motion and tidal stress that stretch or heat their interiors. If the black hole feeds on surrounding gas, its radiation may also alter the chemistry of these developing worlds. Yet even here, in one of the most dangerous zones in the universe, the laws of gravity and matter still allow planets to grow. The cosmos does not limit itself to easy places. Some solar systems contain planets too hot for matter to stay solid. On some worlds that orbit exceptionally close to their stars, nothing stays solid on the day side. Rock vaporizes, iron liquefies, and even the crust becomes a bubbling sea of molten minerals. Temperatures can soar to levels hot enough to melt diamond or strip electrons off atoms, creating an ionized atmosphere more like the surface of a star than a planet. Material evaporates and rains back down, creating cycles of vapor and condensation driven purely by heat. Winds can transport molten clouds to cooler regions where they harden into black glass before sliding back into lava. These planets endure a state of continual transformation, where geology becomes vapor and returns again, rewritten every few days. In their extremes, they stretch the definition of a planet, showing that the universe allows not only solid ground and liquid ocean, but worlds full of boiling stone and metal gas. Some planets shed their atmospheres into space. There are planets so close to their stars or so lacking in magnetic protection that their atmospheres do not remain bound to them. The upper layers of gas expand under intense heat and ultraviolet radiation, rising high enough for stellar winds to sweep them away. This creates ghostly streams of hydrogen, helium, or even heavier molecules that stretch far beyond the planet's normal boundaries. The escape can occur gradually over billions of years, or dramatically if the star emits powerful flares. Eventually, the atmosphere may thin to nothing, leaving behind an exposed surface or metallic core that was once hidden under thick clouds. Such planets show that atmospheres are not guaranteed. They are delicate structures held together only by gravity, chemistry, and the constant tug of a nearby star. And even the most complete and complex sky can slowly break apart and vanish into the dark sea of space. There are solar systems with planets made almost entirely of gas. Some planets in the universe are so vast and lightweight that they are little more than oceans of gas held together by gravity. Their layers are made of hydrogen, helium, or less common molecules like methane, and they lack the solid surfaces we associate with Earth. Deep inside, pressure compresses these gases into exotic forms of matter, including metallic hydrogen that behaves like a liquid metal and conducts electricity. Above these depths, giant storms swirl endlessly, driven by heat from the planet's interior or from the distant light of the star it orbits. Clouds thousands of kilometers thick may form and dissolve over centuries, shifting the colors and temperature of the atmosphere. These planets defy the idea that a world must be solid or even tangible. They are dynamos of motion and energy, spheres where air is both the surface and the depths, and change never pauses. Some solar systems contain more than one habitable planet. A few solar systems are blessed with more than one planet in the region where temperatures allow liquid water to exist. These systems contain multiple Earth-sized bodies orbiting in gentle paths close enough to share starlight and energy, but far enough apart to avoid gravitational chaos. Each planet may have its own continents, oceans, weather, and atmosphere. One might be rich in volcanic activity, another may be covered in shallow seas, and a third may bear thick cloud layers that slowly rain water upon a stable crust. If life arises on one or more of these planets, the others could offer a nearby destination for exploration or communication. Their skies might hold the glowing arc of a neighboring habitable world, visible every night as a constant reminder of shared origins. These rare systems suggest that life might not be alone, even within a single solar neighborhood. We have found planets that orbit so far out, they may never warm enough for life. Some planets orbit their stars at such vast distances that they spend their entire existence in deep cold. Light from the star is as faint as moonlight on Earth, leaving the surface in a state of nearly permanent night. These frozen worlds may have atmospheres, but their gases freeze into the soil, turning the air into frost. Water becomes solid rock, oceans turn into plains of ice, and even the movement of tectonic plates may cease due to the planet's lack of internal heat. With little sunlight to power chemistry or biology, life as we know it has almost no chance to take hold. Yet these planets still hold secrets, such as trapped gases, buried oceans of ammonia, or ancient cores still emitting the last remnants of heat from formation. While uninhabitable, they show us the outermost edge of what a planet can be. Some planets are so dense they must contain more than one core. A handful of exoplanets measure so dense that traditional models of metal and rock cannot explain them. Their mass suggests that they may have formed through the collision and merger of multiple planetary embryos, each carrying its own metallic core. Over time, the cores fused together, while much of the remaining crust and mantle were lost to space in violent debris clouds. Deep inside these worlds, pressure and temperature reach incredible levels, forming strange alloys and crystalline structures unknown on Earth. Their density affects everything from gravity to magnetism. A surface step might feel like a fall, and the pull of the ground would be overwhelming compared to what we know. These planets show the scars of cosmic violence, evidence that creation is not always gentle. Sometimes, worlds are built out of the shattered remains of others. Solar systems can form with no icy objects at all. While we take ice for granted in our solar system, especially in the outer regions and comet clouds, not all planetary systems have it. Some form in environments too hot, too crowded, or too turbulent for ice to freeze during formation. Others form around stars that emit high levels of radiation, evaporating frozen elements before planets can gather them. In such systems, all planets are rocky or metallic, with no frozen reservoirs to balance temperatures or deliver water through impacts. Atmospheres may be thin or entirely absent, and oceans may never form. Landscapes are dry, dusty, and scorched, even on planets that orbit at safer distances. These barren solar systems challenge assumptions about how vital ice is to planet formation. They show that water, one of the most common ingredients on Earth, is not a universal feature of planetary creation. We have found planets with weather systems larger than Earth. Some planets experience storms of unimaginable scale, driven by intense heat, rapid rotation, or thick atmospheric layers. One storm may stretch across the entire circumference of the planet, with winds that travel thousands of kilometers in a single cycle. These systems can last for centuries, fueled by the planet's internal heat or continuous solar energy. Lightning may crackle through clouds hundreds of kilometers deep, illuminating the atmosphere like slow, pulsing fire. Jet streams and high-altitude vortices twist around the poles, carrying energy and material in organized, repeating patterns. In these massive weather systems, the concept of a calm day might not exist. The sky is always in motion, wrapping the world in endless change. They reveal the powerful dynamics that govern atmospheres not only on gas giants, but on terrestrial planets larger or hotter than Earth. Some solar systems contain rogue planets that were captured. A rogue planet is one that formed in a solar system but was later ejected into the emptiness between stars. These wanderers drift for millions or billions of years, frozen in darkness, until encountering another star's gravity. If the encounter is gentle enough, the rogue planet may be pulled into a new orbit and officially become part of a new solar system. These adopted planets often bear the chemical signature of their previous homes, with atmospheres or crusts that differ from the native planets. Their orbits may be tilted or stretched, showing clear signs of the history not shared by their new neighbors. Over time, they may settle into balance or drift again. Their existence proves that solar systems are dynamic, able to exchange and recycle entire planets across cosmic distances. Some planets orbit stars too cold to see with the naked eye. Some stars are so small and cold they emit almost no visible light, yet they can still form fully functioning solar systems. These faint objects, often brown dwarfs or low-mass red dwarfs, glow mostly in infrared wavelengths, invisible to the human eye without specialized equipment. Yet they have enough gravity to gather disks of dust and gas where planets can form. The worlds that orbit them experience dim skies and low heat, even when very close to their stars. Some may be entirely ice-covered, while others maintain thick atmospheres that trap enough heat to liquefy water. Because these stars burn slowly and live far longer than the Sun, their planets have billions of years of stability in which to evolve. These dim systems reveal that starlight does not have to be bright to build planets. Even a star that barely glows can shape an entire planetary family. There are solar systems wrapped in huge clouds of comets. Some solar systems are surrounded by massive reservoirs of icy fragments that extend light years beyond the last planet. These clouds, made of trillions of frozen bodies, are remnants from the chaotic early period of planet formation. They drift far from the warmth of the central star, locked in long, slow orbits that can take millions of years to complete. Occasionally, the path of a comet is altered, sending it inward toward the planets. These cometary visitors may deliver water, carbon-rich compounds, or other essential elements to falling worlds. In some cases, they may also cause destruction when they strike with force. These colossal clouds, invisible in most wavelengths of light, trace the true outer boundaries of a solar system. They represent the past, frozen in place, waiting for time or gravity to bring them back into motion. We have detected planets that orbit in polar paths. Most planets orbit around the equator of their stars, following the same general direction and angle that their stellar disks originally spun. But a few astonishing planets have been found with orbits so steep that they practically loop over the star's poles instead. Instead of circling like wheels rolling on a table, these planets move like spinning tops tilted upright, crossing above and below the star's north and south poles. This strange alignment is likely caused by past gravitational upheavals, such as a near miss with another planet, or the influence of a passing star that tugged the orbit into a vertical path. These near 90-degree orbits can expose planets to unusual stellar radiation and may intensify seasonal temperature changes as the angle of sunlight changes dramatically. They also challenge scientists to rethink how planetary systems stabilize over time. These polar paths show the universe is not limited to orderly, flat systems. Gravity bends possibilities into new shapes, revealing the extraordinary flexibility of cosmic architecture. Some solar systems form with no planets at all, while many stars form with swirling disks of gas and dust that eventually grow into planets. Some never manage to make a single world. In these systems, the disk may disperse too quickly, blown apart by strong stellar winds, or evaporated by intense radiation before the delicate process of planetary formation can begin. Other times, the disk may lack the right ingredients, containing too little solid material to gather into rocky or icy bodies. Some stars are born in crowded environments where gravitational interactions with nearby stars disturb the disk, preventing planet formation entirely. These barren systems may appear calm on the outside, but they represent a brief and unstable childhood where nothing survived long enough to become a planet. Even so, small remnants of dust or debris might linger for millions of years, circling idly with no chance of ever growing. These quiet, planetless systems are reminders that creation requires both time and luck, and not every star wins both gifts. Planets can form in disks with more dust than gas. Most planetary disks contain far more gas than dust, giving rise to giant gas planets, small rocky worlds, and icy fragments. Yet some disks have been found with unusually high concentrations of dust and very little gas. These dusty disks are likely the remnants of violent past events, such as collisions between planetesimals or the breakup of larger bodies that once existed there. In such places, planets may form from dry, hard materials, leading to worlds rich in rock and metal, but poor in atmosphere. The lack of gas also makes formation faster, since particles can clump together without being slowed or scattered by surrounding hydrogen or helium. However, it also limits the possibility of forming gas giants and may leave planets exposed without thick atmospheres to protect them. These dust-dominated disks reveal that not every system begins with the same recipe. Some start with plenty of air and ice. Others are born from the dry bones of earlier worlds. Some solar systems have planets that orbit far outside their star's gravity. A few planets have been discovered in orbits so distant and so slow that they raise questions about how tightly the star actually holds them. These planets may circle at distances thousands of times farther than Earth orbits the Sun, taking millions of years to complete one journey around their star. At such distances, the gravitational pull from the star becomes extremely weak, making the planets vulnerable to being nudged out of orbit by passing stars, drifting clouds of gas, or the faint tide of gravity from T, the galaxy itself. These wide-orbit planets might have formed close to their stars and then migrated outward over eons. Or they may have been captured from interstellar space, only loosely bound to their new parent star. Their existence challenges the simple definition of a solar system. Where does a star's influence end? These distant worlds stretch the border between belonging and drifting, showing the fuzzy limits of gravitational identity. We have found planets that might be artificial in origin. Among the thousands of exoplanets discovered, a few have raised eyebrows for their strange structure, exact symmetry, or repeating signals that do not match natural processes. Some appear to be shaped like perfect spheres in situations where chaotic formation should make them uneven. Others block starlight in a patterned way, suggesting rings, segments, or panels, rather than globes or gas bodies. While natural explanations exist, including shattered moons, dense swarms of debris, or complex cloud layers, the possibility remains that some of these objects could be megastructures or artificial habitats. These discoveries have inspired scientists to create new detection methods designed to spot signs of deliberate engineering, such as unnatural chemical ratios, geometric shadows, or stable orbits that defy gravity without propulsion. We have not confirmed a single artificial planet beyond doubt. But the fact that we are searching for them shows how far our curiosity has come. The universe may hold more than just worlds. It may hold wonders made by minds far older than our own. Some solar systems contain stars too close together for planets to survive. Binary and multiple star systems are fairly common in the galaxy, but not all of them allow planets to orbit safely. In some cases, the stars are so close or so rapidly changing in distance that no stable region exists for a planet to form or remain intact. Any object caught between them may be torn apart by tidal forces, pulled into one star or the other, or flung into space at high speed. Even if a planet manages to form at a safe distance, the combined light and heat from both stars may fluctuate wildly, creating temperature extremes that prevent geological or atmospheric development. These hostile systems reveal the limits of planetary formation. While the universe often builds worlds, it does not guarantee them. Sometimes the dance of two or more stars is so intense, but nothing else can survive in its path. We have detected solar systems with planets that evaporate over time. There are planets so close to their stars or made of such delicate materials that they are slowly dissolving into space. Their surfaces vaporize under the intense heat, and the atmosphere expands into wispy trails that stretch behind them like burnt shadows. Some of these planets lose more than 1,000 tons of gas every second, shrinking in both mass and radius over time. Eventually, only the densest core may remain, leaving a stripped world too small to resemble its original form. This process has been observed through subtle reductions in planetary size, as well as chemical traces of dissolved rock and gas lingering near the star. These worlds, often called evaporating planets, are reminders that even a stable orbit does not guarantee safety. A planet can hold its shape for billions of years and then begin to fade, grain by grain, into the vacuum. Some planets are too young to have solid surfaces. Newly formed planets can remain molten for millions of years after birth. The heat from their formation, combined with the energy of ongoing collisions and the decay of radioactive materials, keeps their surfaces in a constant state of liquid flow. These young worlds may glow faintly in infrared light, like tiny embers cooling in the dark. Their atmospheres are thick with steam, rock vapor, and sulfur gases, where clouds are made of droplets of molten metal or glass. Beneath these skies, the planet may still be gathering mass, absorbing smaller bodies that strike its surface and add energy and chemicals. Only after time, cooling, and balance can a crust form, hardening into continents and floors for oceans. These fiery planets offer a glimpse into Earth's past, when our world was a ball of glowing liquid turning slowly in a black sky, waiting for the first layer of stone to cool and still. There are solar systems that are nearly perfectly symmetrical. Some star systems are arranged with an almost uncanny order. Planets orbit at precise distances that reflect balanced ratios. Moons arrange themselves in repeating patterns, and orbital periods lock into harmonious timing that repeats like clockwork. These symmetries are not accidents. They are the result of long-term gravitational interactions, where planets exchange small pushes and tugs until they settle into patterns that minimize disruption. Such systems can survive for billions of years without collision or scattering, preserving alignment even when the star ages or nearby objects pass by. Their beauty is not just visual but mathematical, showing how the laws of motion can create elegance without conscious design. These systems reveal the quiet intelligence of physics, weaving balance into matter and motion on scales too large for the human eye to see. Some planets have oceans of liquid carbon dioxide. On certain worlds with the right pressure and temperature, carbon dioxide does not behave as a gas or a solid, but as a dense, flowing liquid that can pool into oceans. These seas may stretch across entire hemispheres, shimmering with frozen fog at the surface where cold air brushes against the dense fluid below. Beneath the surface, temperatures and pressures rise, dissolving exotic chemicals and creating strange conditions where life might exist in forms unknown to Earth. Volcanoes may release geysers of liquefied carbon dioxide that fall again as freezing rain. Waves may carry fragments of mineral ice instead of water. These planets remind us that oceans do not always mean water, and habitability does not always mean sunshine and blue seas. The universe has many ways to shape its worlds, and some of them include seas of invisible gas transformed into rolling tides of unfamiliar chemistry. We have detected solar systems with planets on million-year orbits. Some planets orbit their stars so slowly that they take more than 1 million Earth years to complete a single revolution. These distant giants travel on paths so wide that their parent star appears no brighter than a brilliant speck in their skies. They feel almost no warmth from starlight, and instead rely on internal heat left over from their formation to generate geological or atmospheric activity. Ice and rock make up much of their mass, compressed into layer after layer of frozen crust and mantle. The gravitational tug from neighboring stars, or even the galaxy itself, can subtly influence their orbits over millennia, stretching or shaping their paths into long, slow arcs. These worlds challenge our understanding of time in planetary science. Their years are so vast that continents could rise and fall, atmospheres could thicken or vanish, and entire civilizations could appear and disappear during a single orbit. They remind us that time itself is relative to motion, and some worlds live in cycles that dwarf all earthly history. Some solar systems have planets too heavy to be made of rock. We have detected planets with densities and masses so great that they cannot be composed of ordinary rock or even iron-rich cores. These superdense planets are thought to contain exotic materials compressed into forms that do not exist naturally on Earth. Some may be made of degenerate matter, similar to the cores of dead stars, or formed from the remnants of shattered giant worlds. Their gravity is so intense that atmospheres collapse close to the surface, forming oceans of superheated gas or metallic rain. At their centers, pressures can reach levels that fuse atoms into strange lattices or create new phases of matter. These planets are like cosmic anvils, forged in the most extreme conditions of early solar system formation or violent collisions. They prove that there is no single recipe for a planet. Some are too dense to fit familiar categories and reveal the boundless creativity of gravity and time. planets can form from the remnants of colliding moons. Sometimes planets are not born from single disks of gas and dust, but from the shattered remains of moons that collided in catastrophic impacts. When two large moons crash together with enough force, they eject clouds of molten rock and debris that can coalesce into entirely new bodies. Over time, this material cools and forms layers, becoming a planet with a unique structure and composition very different from the worlds around it. These collision-born planets may lack certain elements found in their parent stars, or contain unusual mixtures of silicates and metals from both original moons. Their orbits may be tilted or irregular, reflecting the chaos of their formation. They represent the second generation of planetary evolution, proving that the cosmos recycles its matter in ways both violent and beautiful. Even destruction can create something new when the universe rearranges its building blocks. Solar systems can change shape over billions of years. Planets, stars, and debris do not remain fixed in place forever. Over time, solar systems can stretch, fold, or transform as the forces of gravity, stellar evolution, and external influences reshape their structure. As stars lose mass through radiation or stellar winds, their gravitational pull weakens, allowing planets to drift outward into colder, quieter orbits. Nearby stars or passing molecular clouds can distort the system's outer boundaries, nudging comets inward and scattering moons or asteroids into new regions. Even within the system, interactions between planets can change orbits over eons, shifting conditions so gradually that the planets themselves may not endure long enough to notice. These long-term changes reveal that stability is a temporary state. Solar systems breathe and evolve, just as stars do. Nothing in space stays fixed. The quiet clockwork of the night sky is alive with unseen motion on scales far greater than a human lifetime. Some planets are so puffy they could float in water. A strange class of planets known as superpuffs are so low in density that, if a large enough ocean existed, they could theoretically float. These worlds are often similar in size to Jupiter, but contain only a fraction of its mass. Their atmospheres are inflated by heat and low gravity, creating layers of fluffy gas that extend thousands of kilometers from their core. These outer regions are so tenuous that sunlight can pass through them, allowing astronomers to study the chemical makeup of the upper clouds. Superpuffs may form early, near hot parent stars that heat their atmospheres before they can contract, or they may migrate outward after forming, preserving their softness in cooler regions. They challenge our expectations of density and scale, reminding us that not all planets are firm, weighty spheres. Some are more like floating balloons, delicate shapes in the vast oceans of space. We have found planets that orbit so slowly they barely move. Some planets orbit so far from their stars, but an entire human civilization could rise and fall before the world completes even a tenth of its path. A single orbit may take hundreds of thousands of years, or even longer. On such planets, daylight changes imperceptibly. Seasons last for millennia, and temperature shifts are slow enough that geological change outpaces weather. Time on these worlds feels nearly frozen, a faint blur measured only by shifting stars in the sky. Their distances make them immune to most stellar storms or magnetic activity, but leave them exposed to cosmic rays and drifting interstellar clouds. Life, if it exists there, must evolve without sunlight or rapid change. These slow-moving planets reveal how vastly different the flow of time can feel from one world to another. For them, a year is not a cycle. It is an era. Some solar systems hide planets behind their stars. There are planets we can only detect intermittently because they orbit in such a way that they remain hidden behind their parent stars for most of their paths. These worlds are nearly invisible, masked by the glare of the star whenever we try to observe them directly. We infer their presence from gravitational tugs, faint changes in starlight, or tiny distortions in the movement of other planets. In some cases, the angle of the orbit keeps the planet perfectly aligned with the star, leaving only the faintest trace of motion to reveal that something is there. These hidden planets show that our view of the universe is naturally limited by geometry and light. Much of the cosmos is concealed by its own brilliance, and entire worlds could remain unseen for millennia unless we learn to watch for their shadows. There are solar systems with planets that never see their sky. Some planets are covered in such thick cloud layers or atmospheric haze that the sky is permanently obscured. Their surfaces are wrapped in darkness or diffuse glow, with no stars, no constellations, and no sight of the sun or galaxy beyond. The atmosphere scatters all visible light, creating an eternal fog where day and night feel eerily similar. Some of these planets are hot, filled with boiling clouds of sulfur or carbon-rich gases. Others are cold, wrapped in methane smog that never clears. Surface dwellers, if any exist, would have no natural way to understand the scale of the universe. They would live and die under a ceiling of mist, unaware of the stars above. These worlds reveal that not every planet shares our view of the cosmos. Some are sealed inside their own atmosphere, with nothing but weather and wind to remind them of the sky. We have detected solar systems forming in binary star systems. In some regions of the galaxy, two stars orbit one another while planets form around them both. These binary star systems can create complex gravitational landscapes, influencing the disks of dust and gas in ways that lead to unusual planetary orbits. Some planets circle both stars in a stable, wide orbit, experiencing double sunrises and sunsets. Others orbit just one star, with the second star appearing in the sky as a bright and shifting presence. The interplay of gravity, radiation, and motion shapes the way planets grow, sometimes creating tilted orbits, dense asteroid belts, or broken disks where matter never settles. These systems expand our sense of what is possible in planetary science. Not all solar systems are built on a single star. Some are born from pairs, where balance and beauty arise from doubled light. Some solar systems have stars that steal planets from each other. In crowded star clusters, close encounters can cause stars to tug planets out of each other's orbits, stealing or scattering them like celestial pickpockets. When two stars pass near one another, their gravity can pull a planet into a new path, stripping it from one star and placing it in orbit around another. These captured planets may retain the chemical or atmospheric signatures of their original star, revealing their stolen past. Others may be flung into space entirely, becoming rogue planets. The process is slow and silent, but it reveals the competitive nature of stellar formation. Solar systems are not sealed. They share and lose planets in the ever-shifting web of galactic motion. These cosmic thefts show us that planets are not permanent belongings. They are pieces of a dynamic puzzle, always in motion, always subject to the pull of other stars. Planets can form in disks of pure ice. In the coldest regions of space, beyond the reach of starlight or heat, particles of frozen water, methane, and carbon dioxide can collect into disks made almost entirely of ice. These icy rings surround young stars or even planets, forming stable structures where gentle collisions gradually fuse grains into larger chunks. Over time, these frozen particles clump and bond, building planetesimals that grow layer by layer into solid ice worlds. The absence of dust and gas means these planets may contain few rocky materials or metals, making them some of the most pristine bodies in the universe. They may remain frozen for billions of years or warm later if they migrate inward. Some may develop underground oceans when internal heat melts the lowest layers. These icy planets reveal that not all worlds begin with fire. Some are born from silence and cold, sculpted entirely from the frozen breath of interstellar space. Some solar systems have their own mini black holes. In rare cases, a star may form near the remnants of a long-dead giant. A black hole, so small it exerts just enough gravity to sit peacefully within a new solar system. These mini black holes may be relics of ancient explosions or the collapsed cores of early stars that burned out before the present system took shape. Their gravity can influence the movement of planets and debris, creating strange orbits or clearing gaps in the surrounding disk. Some may accrete tiny amounts of gas or dust, giving off faint X-ray signals detectable from great distances. Their presence challenges nearly every model of solar system formation. A system that contains a black hole and a living star together defies the usual cycle of life and death in the cosmos. These environments show that solar systems are not always isolated stories. They may inherit the shadows of the past and evolve around them. We have found planets that exist only as molten lava. Some planets are located so close to their stars, or formed so violently, that their entire surfaces remain oceans of molten rock. Temperatures may reach thousands of degrees, hot enough to vaporize metals or turn stone into glowing rivers. These worlds often have no atmosphere, since gases cannot condense or remain bound to the surface in such intense heat. Any exposed material melts and flows, reshaping the planet continuously as tides of lava rise and fall under the pull of gravity. From space, these planets shine with infrared light, their molten surfaces flickering like coals in a furnace. They may cool if they drift farther from their stars, but many are locked in permanent fire. These inferno planets remind us that the universe does not guarantee stability. Some worlds are made not to grow or host life, but simply to burn in silence for all of time. Some solar systems may form entirely without water. While water is abundant in our solar system, it is not guaranteed in every planetary nursery. Some stars form in dry regions of interstellar space, where hydrogen is plentiful, but oxygen-rich materials are scarce. In such environments, planets may form from dust, metal, carbon, or silicates, with almost no ice to deliver water later. These planets may have no oceans, clouds, rivers, or atmospheres shaped by evaporation. They might be covered in sand, jagged rock, or volcanic fields, with nothing to smooth their surfaces over time. Life, if it exists, would have to depend on solvents other than water, or on chemical reactions driven by heat and minerals. These waterless systems reveal that Earth's moist conditions are not universal. Many worlds may never know rain, never hear storms, or never carve canyons with flowing liquid. Their landscapes are sculpted by fire and dust, not water and wind. Some planets form at the edge of interstellar space. Not all planets form close to warm, bright stars. Some emerge in vast, cold regions at the edges of molecular clouds, where starlight is faint and gravity barely binds the gas and dust. In these distant places, particles collide slowly and gently, sticking together over millions of years without being vaporized by heat. The resulting planets are often small, icy, and slow-moving orbiting stars so far away that light and warmth can take centuries to reach them fully. Their skies are dark even at midday, filled not with blue, but with deep, muted gray. Yet beneath their frozen crusts, pockets of warmth may linger from internal radioactivity or the pressure of accumulated mass. These edge worlds remind us that planets do not only form in the glow of suns. They form in shadows too, patient and quiet, waiting for light they may never receive. There are solar systems with sunless inner regions. Some stars are surrounded by thick rings of dust or gas that block light from reaching the innermost planets. These planets orbit in permanent twilight, warmed only by faint, indirect radiation or the heat of their own formation. They may never experience sunlight on their surfaces, and their skies might appear as dim, foggy voids without stars or shadows. Over time, the dust may drift outward or burn away, revealing the star in sudden bursts of illumination that change the surface conditions dramatically. But while the darkness lasts, these planets live in near silence, untouched by the kind of solar energy that drives weather, photosynthesis, or climate cycles on Earth. These shadowed systems remind us that light is not guaranteed. Even with a star at the center, entire regions can remain cloaked, waiting for the universe to shift its curtains. We have detected signs of planets shaped like footballs. Gravity usually shapes planets into near-perfect spheres, but intense tidal forces from a nearby star or massive neighbor can distort a world into an elongated form, stretched along the line of gravitational pull. From a distance, these planets resemble cosmic ovals, with bulging equators and compressed poles. Their surfaces strain under the constant force, creating volcanic activity, shifting crusts, or deep ocean tides that never settle. The atmosphere may thin in stretched regions and thicken in compressed ones, creating extreme weather that varies minute by minute. These football-shaped planets may eventually return to a spherical form if they drift farther from the force that deformed them. Or they may shatter from the strain, leaving behind rings of debris. They reveal that even the most fundamental rule of planetary shape can be bent by the right kind of pressure. Solar systems can be born from stars too massive to live long. Some stars are so enormous that they will burn through their fuel in just a few million years. Yet even in that short time, their surrounding disks can give birth to planets. These solar systems are doomed from the beginning, fated to destruction when the star collapses into a supernova. But while they last, they may host giant planets, molten moons, and rings of glowing dust, stirred by powerful radiation. Life is unlikely to evolve in such violent conditions, but the brief existence of these planets still matters. They may seed the galaxy with heavy elements when the star explodes, spreading the ingredients for future solar systems across space. These short-lived systems remind us that not all cosmic stories are long. Some unfold like bright sparks, fierce and brief, creating and destroying worlds in mere cosmic moments. Some solar systems are so young they still glow. In their earliest stages, solar systems are illuminated not just by their stars, but by the heat of their own formation. Dust, gas, and newborn planets radiate in infrared light, heated by constant collisions and the slow compression of raw materials into solid bodies. Even the planets glow softly, lighting their own skies before cooling into darker worlds. These systems are warm cradles of creation, where chemical reactions race ahead, weather has not yet formed, and surfaces remain molten or unstable. Their light is not the steady shine of maturity, but the flicker of origin. They appear to us through telescopes as red-tinted clouds, full of promise and potential. They offer a glimpse of what our solar system must have looked like before its planets cooled, before oceans condensed, and before crusts formed to seal in the secrets of early time. The study of solar systems is helping us discover how rare Earth might truly be. By comparing hundreds of planetary systems across the galaxy, scientists are discovering just how unusual Earth may be. Many systems lack rocky planets or contain only giants made of hydrogen and helium. Others orbit multiple stars, experience intense radiation, or lack key ingredients like water or carbon. Some are too young for life to evolve, and others are so old that any habitable worlds might already be gone. Earth lies in a narrow zone of balance, with the right star, the right orbit, the right composition, and the right timing for life to develop and endure. Studying other systems does not diminish our place in the cosmos. It expands it, showing how precious and precarious a world like ours may be. The more we learn, the more clearly we see the truth. We are not just a planet among countless others. We are a rare kind of story. Thank you for drifting through the endless quiet of the cosmos with me tonight. As we wandered together from one solar system to the next, we saw just how strange and beautiful the universe can be. Worlds of ice and fire. Stars that share their light across impossible distances. Planets that form, dissolve, collide, and begin again. Every system, a different story. Every orbit, a gentle turning of time. If you enjoyed this quiet journey through the stars, I invite you to like, subscribe, or share a thought below. It helps other curious dreamers find their way here, one sleepy soul at a time. But for now, let all that drift away. Let your breathing slow. Let your mind loosen its orbit, floating free like a comet through still, silent dark. The universe will keep turning without you for a while. You have done enough for today. Close your eyes, rest, and dream of other skies. Good night.